Welcome to Structural Analysis 2 video series, unit number 4, Stiffness method. Lecture outline, numerical on rigid frame. Problem statement as follows. Analyze the rigid jointed plane frame supported and loaded as shown in figure by stiffness method. Draw bending moment diagram. Now in the given figure of rigid jointed frame is given. AB is a column loaded with 25 kN per meter UDL and the length of AB is 4 meter. A is a fixed support. BC is a beam having a length of 3 meter and loaded with the 50 kN point load at the midspan. Column CD of a length of 3 meter loaded with the 40 kN point load at a distance of 2 meter from C and 1 meter from D side. Here at D, instead of hinge, here consider fixed support. Okay, otherwise the unknown will get increased. So instead of hinge here at D, consider fixed support. Now the first step, a degree of kinematic indeterminacy dki or a degree of freedom is equal to 3. Why 3? Because at B there will be a rotation and at C there will be again 1 degree of freedom, which is in term of rotation. So there is rotation theta B and theta C at B and C. Also there is no any support for the transverse direction at B and C. So column will sway toward the right side, let us assume. So delta will be there. So there are 1, 2 and 3 unknowns. So degree of freedom will be a 3 delta theta B and theta C. So this is a sway type of problem. Now assign the coordinate, second point, assign the coordinate direction to the unknown displacement. So let's say d1 is equal to theta b and that will rotate in anti-clockwise direction, positive. d2 is equal to theta c, anti-clockwise, positive, and delta 3 is d3 is equal to delta, which is right side, let's consider as a positive. Okay, so these are the signs or coordinate directions that we assume here. Next point, uh, external force or moment acting in the coordinate direction that we have to see, and we call it as ADL. So there are 3 unknowns. So there is no any external moment acting in the coordinate direction theta b. So ADL1 is equal to 0. Now second coordinate is theta c, but there is no any external force acting in the coordinate direction second or theta c. So AD2 is equal to 0. There is no any external force given on the member in the direction of delta or third coordinate direction. So AD3 is equal to 0. So there is no external force or moment acting in the coordinate direction. So the value of AD1, AD2, AD3 is all are the 0. Next step, force in the coordinate direction of a restrained structure ADL. To find out the ADL1, ADL2 and ADL3, we have to keep each member restrained and find out the friction moment. Now first is a column and acting with the UDL of 25 kN per meter. So friction moment will be WL square by 12. So we have 33.33 as a friction moment for each end. Now there is a point load acting at midspan and friction moment will be WL by 8 and the value will be that value will be 18.75 for each end, and the for the next span which is a column, that is a CD, point load is 40 kilonewton and which is acting at 2 meter from C and 1 meter from D side. So the friction moment will be WAB by L square. So it will be W for this side, if this is A and this one is B, it will be W AB square divided by L square, and it become 8.89 here, 8.89. And for this side it will be WA square B divided by L square, it will be uh, 17.77. Okay, so now we are interested in the coordinate direction. Our first coordinate is theta b here, and second coordinate is here, theta c, and one more coordinate which is a horizontal delta. So in that direction, the forces acting by keeping a structure restrained, that we have to find out. Let's find out at one. So at one location, there are two fixed moment acting for a span AB and span BC. So first is minus 33.33. So take that, and second is this one, 8 plus 18.75. So plus 18.75. So net is minus 14.58. Now second location, second coordinate, this is our second coordinate where theta c is our unknown, and the fixed moment is minus 18.75 for BC and C, and next is for C end of CD column, the moment is 8.89, and the net will be minus 9.86. Now there is also delta which is acting axially uh, along the length of a BC, but we always neglect the axial force of a beam. So there is a reaction from the column, that due to the loading, that horizontal reaction we have to consider, which is acting at the B. So that reaction will going to that reaction will act in the direction of delta. So neglect the axial reaction due to the beam, only consider the axial or horizontal reaction due to the loading at B and C of a column, that we have to consider. So separate a bit is drawn here, and the loadings shown there. So first load is a 25 kilometer per meter. So reaction on due to the loading on each end will be half 25 into 4 divided by 2, it becomes 50 kilonewton at each end. Now similarly find out reaction due to this 40 kilonewton. Uh, so there is a 40 kilonewton acting 2 meter from C and 1 meter from a D. So to find out reaction here, we have to, like, for this one is A and this is B. B is equal to 1 and A is equal to 2. So to find out the reaction, we have to do 40 into B divided by L. You will get 13.35, and to find out 26.67 reaction, you have to do 40 into A divided by L. You will get this 26.67. Okay, so now we know the reaction at B and C. So these two reaction we have to consider. So one is positive toward the right side, and this one is a minus toward the left side. So minus 50 plus 13.33, it become minus 36.67. So these are the uh, ADL1 or ADL2 or ADL3 value which are acting in the direction of coordinates. Okay. Next point is determine the stiffness matrix S formed by the forces in the restraint structure subjected to unit value of D1, D2, D3 corresponding to unknown displacement. Now unknowns are 3, so matrix size will be 3 by 3. So these are the column 1, 2, 3, and these are the row number 1, 2, 3. So first is your first row, you see there is in each row of a matrix, first is a row number 111, and then there is a column number 1 2 3. Again in a second row you see there is a row number 2 is the first 2, and after that there is a column number 2 1 2 2 2 3, and in last row again there is a row number 3 is the first number is a 3, and after that there is a column number 1 2 3. So likewise you have to write down. Now apply the unit rotation for d1 is equal to theta b is equal to 1 in anticlockwise direction as a positive. Now here due to the presence of delta, one additional term will be there. Let's see on the column. Let apply the unit rotation at theta b. When we apply in the unit rotation at theta b, now before that let write down the coordinate. Coordinate is 1, and then second coordinate is theta b. First is theta b, second is theta c, and one more coordinate, that one is a delta in this direction, let's say 3. So now we are applying a unit rotation on the column AB. So and by keeping this far end fixed, so only B is allowed to rotate by unit rotation. So when we allow B to rotate, it will rotate and the adjacent both member will rotate like this. So due to this rotation happen, both moment will happen on the both members beam and column, which is connected at the B in the coordinate direction 1. So they will be 4 ei by L for BA plus 4 ei by L for BC. So by putting their length, moment of inertia is I for all members. We have 2.33 EI. Now second coordinate is here theta c, and half will be carry here, so it will be 2 ei by L CB, and the length of CB is or beam is 3 meter. By putting that we have 0.67 EI. Now third coordinate is delta. Now when we rotate this now delta, there is a reaction uh, on the column that we have to consider. So this column will not move because we fixing here when we allowing the rotation, the fixity is at far end. When we are allowing rotation at B, there is a fixity at the far end. So due to that, this column will not move or rotate, but this column will rotate. As is rotate, this moment generated 4 ei by L, and here is uh, 2 ei by L. So to counterbalance these two moment, the reactions also generated in this direction. So these reaction create the moment in the opposite direction to this rotation. Okay, to balance this moment which is at the end. So these reactions are in a magnitude, and that magnitude is 6 ei by L square. So these reactions, here is a reaction which in the direction of this delta on the column, and that is 6 ei by L square. So take that reaction. Now only that is for this AB column. At B we have to consider only because in the direction of B delta is there. So 6 ei by L square BA for the column BA. So putting the value of length of a column BA is 4 square is equal to 0.375 EI. Okay, so we will get the first column of a matrix by applying unit rotation for theta b is equal to 1. So remember, whenever there is a delta due to the rotation of a column, the reaction generated, and that reaction is 6 ei by L square, okay, in the direction of a delta. Now apply the unit rotation for d2 is equal to theta c is equal to 1 in a anti-clockwise direction, and keep the far end fixed. Now keep this far end fixed and apply unit rotation at c in an anti-clockwise direction. So this is a rotation will happen for each member, and that will be, now we are applying at d2. Before that, let write down the coordinate location 1, 2, and one is delta is there. Now we are applying the for 2, so we will get the these are the coefficients. So first one is let's find out 2 2. So when we are applying the unit rotation, second number here which indicate the action happening at location 2. Okay, and first number indicate the location of coordinates. So when we apply the unit rotation here, both member rotate, and that rotation is always 4 ei by L for CB and for CD, beam and column. So putting the length of each one, length of a beam is 3 and length of a column is also 3. So we have moment of inertia is constant. We have 2.67 ei. Now at the far end, half moment will be carry, and that one is 2 ei by L, and that we know the coordinate is rotation. So 2 ei by L will be the moment, and length is 3. So it become 0.67 ei. Now when we are applying a rotation here, we know that there is a reaction on the column. Reaction on the column, and these are the reaction. So this moment is 4 ei by L square, and here is half 2 ei by L, 2 ei by L, here is not square, 4 ei by L, 4 ei by L and 2 ei by L, and this reaction is always, if this length is L, this reaction is always 6. If we say this is a reaction, and to find out this reaction, you have to add this together, 4 ei by L and 2 ei by L, it become 6 ei by L, and is equal to, this reaction should create the moment R into L. So take this L toward the left hand side, it becomes 6 ei by L square. So this reaction is always 6 ei by L square. So you simply remember the reactions are there in case of a delta, and that reaction is always 6 ei by L square. So there is reaction, and that value is always 6 ei by L square, and that we only consider where our location of delta. So delta is in the direction of axial direction of a beam, or along the length of a beam at the end of a C for CD, not for this column, because this end is fixed, so no translation happen for the column. Only CD column, the C end, there will be reaction, that is always 6 ei by L square. So putting the value 6 ei, length of a column is 3, we have 0.67 ei. So we have a second column of a matrix. Now next apply the rotation in the direction of now here now third unknown is, or coordinate direction is delta. So rotation is not here. Now here you have to apply the translation toward the right side as a positive. So let apply the translation for the column. So both column will move toward the right hand side. So when we applying the translation to the column, delta is equal to 1, or unit translation toward the right side, the moment is generated at end, that moment is always 6 ei by l square, and the 6 ei by l square for the both end, it is always 6 ei by l square. When we apply the translation to the column, these moments are 6 ei by l square, and due to these end moment, these are the 6 ei by l square, that there is a reactions at each end, and that reaction is 12 ei by l 12 ei by l cube. So these two things we have to remember, that when we apply the translation to the column, the moment generated at each end, that moment is 6 ei by l square, and the translation which is reaction in the direction of delta at each end, that reaction is always 12 ei by l cube. Okay, so let write down now. The first is applying a delta to the column end. So the moment will generate, this is one location, one coordinate, and due to the delta will be there for both column, and due to the delta the moment will generate at second location, and there is a reactions, okay, in the direction of 3 or delta from the both column. Now delta will be for both column, and the axial deformation of a beam is neglected. So the action happening in the direction of 3 now, third coordinate. So due to the delta is equal to 1, what happen at 1, 2, 3, that will form a third column of a matrix. At 1, 3, there is a moment, and that value will be 6 ei by l square. Okay, so putting the value, and that is a column end is rotating, so length of column is 4, moment of inertia is I, it become 0.375 ei. And for 2, 3, at coordinate 2, due to the unit rotation in the coordinate 3, what happen, again the end moment will generate, that is 6 ei by l square, that is for this column CD, length is 3, we have 0.67 ei. And then there is a reactions in the direction of a coordinate 3 for the both end of a column, so that reactions are always for both end of a column, so reaction is 12 ei by l cube plus 12 ei by l cube for AB column and for CD column. So putting the length of that each column, AB is 4 meter and CD is 3 meter, we have 0.64 ei. So we have now the third column of a matrix. Then the assemble the all the equations and form a superposition equation of equilibrium. Okay, so let we stop here, and remaining part will be resumed in the next lecture.